Recording.
It's already there on YouTube. Yeah. Hello. Good morning, everyone.
Good morning to all of you. Recording. So we'll be starting our first day of our first workshop.
Yeah, and it's enterprise. And I hope you've already seen that basically Astro Sprint consists of 3 workshops. This is our online one, which is enterprise. And we hope the next one will be offline, which is in July, discovery. And then we'll have next gen in November, right? Let's see if the COVID situation seems to improve, we can maybe push it in from July to a little later so that we can try to still do offline session. And
and the idea behind this, as you must have seen, is with the first workshop, we introduced you to various areas of research, slightly different from what you did in archival data. The mentors, some of them are same. They volunteered to be with us again because they were very happy with performance of the participants, most of you. And you have to be in touch with them through the forums which are there on our website, which Priya will just show, and continue your work and present it in the next workshop and when we meet in person, hopefully. Okay, so
yeah, so I'll just briefly introduce you to the website. So the website, which obviously all of you all have seen and registered, is the Astro Sprint one. And what we've done this time is, instead of making, all of us last time when we work on projects, we all had different WhatsApp groups and, different ways of communication. This time what we decided is better to consolidate all the communication as well as document it, right? So that it's all available to everybody at all points of time. And that is why what we've done is, if you actually see on our website, on the Astro Sprint website, yeah, is that this time what we've done is we have actually created a blog, as well as, I hope you all can see the website over here, and I hope you all like the website. I hope most of you all are Star Trek fans. And if you actually see over here, there is something called the forum, right? And if you click on the forum, first of all, okay, you all need to create a login. So everybody should preferably create a login of themselves, so that then you can participate in the forum, right? So now if you have a forum, once you have your account, you can create a new post, right? And we can have actually discussion threads based on whatever you find interesting, right? So like you can see, you can create a new post, right? And you can put up your things. And we hope that in this way, like in normal forum websites, there'll be a chain with a certain thread, right, for discussions, which people can continue on and which is documented and kept over here, right? And therefore, please try to, let's try to do most of our interaction through the forum. And the idea is the 3 days now we have the workshop, right? But after this, you're obviously going to continue with your work. And while you're doing that work, interact via the forum, which has been created, right? There's also another thing called links and resources. And at present, I have just now put one link. This is Tarundeep Saini, who's going to take 3 afternoon sessions on stats, on statistics for all of you all. He's actually created an excellent document. If you click on this, you'll actually see he's created a nice 23-page document itself over here on the basics and stats, right? And that's obviously a very important component of data analysis. So it's a good thing to do it well. So in short, you will also have this link, which I have to, to the links and resources. And as we progress, I will add more links over there. So you will get links and resources. Like, for example, today when Tim Hamilton does it, he already has his chapter ready. We'll be putting that up over there. So let's hope that this time we can, organize all our stuff in a much more better way than we did it in astronomy from archival data, right? So we'll start with our first talk today. Yeah, and like Sir mentioned, we have made an attempt that we do not repeat anything that happened last time. But it is not necessary that you watch all the videos to understand everything this time, excluding, for example, Python. Python and AstroPy you will need, right? So if you don't know Python and AstroPy, I suggest you go through it a little bit because that may be used by some of the speakers. But other than that, all the topics will be new topics, newer areas, right? So we'll start with our session today.
They will be new in some way, but also a continuation. It's going to build up on what you have learned. And you all are welcome to continue with your previous problems with your previous mentors and also with this. Okay, so let's hope that we have a successful session. We have good speakers with us, and you'll have to be attentive these 3 days. Okay, so we'll start off with the first talk on N-body simulations and applications in astronomy. Yeah, so where do we begin? Do I start with the equations or these beautiful pictures? And I think the best way to begin is at the beginning. We'll see what are the lessons we have learned from stars. Stars have taught us to see patterns in nature. They rise and set in a very specific way, maintaining their constellations, shapes, and so on. They show us a regularity, a perfection of movement, and there is predictability. These are very essential things in method of science, where you see patterns, you see with what things are regular, what are irregular, and try to explain them. And you try to predict using what you have seen and see whether your predictions come through. And if it is, then you have understood why a certain thing is occurring the way it is. So the heavens inspired the great thinkers to usher in the modern scientific revolution. By the time of Galileo, Tycho Brahe, Kepler, Newton, the modern scientific revolution had begun. The modern scientific mind was a driving force. Falling bodies and motion and so on. And works of Galileo and observations of Tycho Brahe led Kepler and finally Newton to formulate the laws of mechanics, the law of gravitation. And Newton was the first of the modern thinkers. Right? He had also with him certain elements of metaphysics and alchemy, which was practiced earlier. But then with Newton, we come to universal laws. We realize the same laws which hold on land, hold out there in the universe. And there was a way to probe and understand things which were much beyond our reach and control. So in these patterns and regularity, there were some irregularities, right? When they saw these bodies move across the sky, there were a few objects which did not stick to the perfection of movement of the stars. And these were the wanderers. And these are the planets which we understand today. So the planets do show some kind of a retrograde motion. Sometimes you see them moving across the sky towards the northeast, and suddenly against the backdrop of the stars, and suddenly you start seeing them moving in the opposite direction and so on, right? So basically, the reason was is that these objects are much closer to us, and their relative motion does get expressed in our day-to-day observations, while for stars which are much further off, their motion we don't perceive in long intervals of time. So, coming to the beginning, yes, there was at that time people realized why the planets are moving around the sun, and Newton gave the theory of gravity and said that there is a force between any two masses which attracts them. Motion of these planets. And Newton's laws were also very successful in predicting objects which were not seen earlier, Neptune, Pluto, and so on. Uh, but the one question which troubled the astronomers was, is the solar system stable? So they had a very good idea after Newton of the solar system. It was very clearly established that the sun is at the center, which is the prime force of gravity, and the gravity of the sun is forcing these objects to move around it in elliptical orbits, and the reasons for that. But the question was, is the solar system stable? And this is formulated in a mathematical problem which is called the N-body problem. So what is the N-body problem? The N-body problem is stated thus: the study of motion of N bodies moving under mutual gravitational attraction. So suppose you have N objects, M1, M2, M3, Mn. We know their positions and we know their velocities. We want to predict where would they be after a certain while. And this sounds like a very simple problem. It is very simple in the sense of writing the equations of motion. The equation which we see here gives you the equations of motion for these n bodies. I goes from 1 to n. And what we have is we use Newton's law of motion. Newton's, we use Newtonian mechanics, in which we uh, basically use uh, second equation, and let me see if I can. Okay, right here. Yeah, so we have mass into acceleration. Yes, the two dots indicate the second time derivative. dr by dt, we denote it as ri dot, and the second derivative with respect to, we use I double dot. So mass into acceleration is the force, and the force which is experienced by ith particle is due to the m I mj. Rij is the unit vector in this direction of from I to j, and Rij square, and we sum it from j going from 1 to n, but keep in mind that j should not be equal to I. Whenever I takes a certain value, when I is equals to 1, then j will go from 2 to n. When I takes 2, it goes 1, skips the 2, and 3, 4, and so on, because there is a particle or a mass does not attract gravitational force on itself. And good thing it doesn't, otherwise the denominator, the distance between a particle with respect to itself would become zero, and this would blow up. It would be infinite force, right? So if I convert this from unit vector into a vector, then I change this to cube. So hence we get this equation Ri, yeah, and this mi and mi on both sides are removed. So we are writing without the mi's here. This Rij indicates the distance. It is the modulus of Rij, the vector. Okay, so Rij. So it's very easy to write these equations of motion, but to solve this is quite an issue. Okay, and I is equals to um, 1 or 2, then things are fine. But the moment I becomes greater than or equal to 3, you do not have a general solution to these equations, right? So this brings us to, oops, yeah. So this brings us to uh, the three-body problem. So what is the three-body problem? When you substitute n is equals to 3, we have the study of motion of 3 mass points moving under their mutual gravitational attraction, right? So this three-body problem is a formidable problem. It has a history of over 400 years, and the best of mathematicians from Newton's times to today have worked on the three-body problem. And in 1850s, 1857, Poincare showed that he gave a theorem which said that if those conditions are satisfied, you would not find a general solution for this. And Bruns went about to prove that you cannot find a general closed form solution for the three-body problem. But then, uh, what is possible is is you can find particular solutions. Yeah. So three-body problem is a well-posed mathematical problem. It's very easy to obtain the equations of motion. We have the study of motion of uh, just just a word of caution. Uh, in this should be an arrow, not a cap. Yeah, this is a not a unit vector, but because I have r cube already in the denominator. So it's very easy to obtain equations of motion. Uh, but it's a formidable one. It has played the central role in celestial mechanics for over 400 years, and it has tremendous amount of applications. Most of the lunar theories are based on this. Artificial satellites are launched using the three-body problem. Even the impact orbits landing on Mars or landing on Mars or the moon, or they work on the three-body problem. And what Poincare went further to establish was, though you do not have uh, a general solution for the three-body problem, but it has numerous particular solutions. We have particular solutions, and he showed that if the particles move in such a way that they maintain their geometry all the time, then you would repeat their motion again and again, and you can get all kinds of various complicated uh, uh, periodic solutions. But what we don't have is a general solution, right? So, so what do? We have to solve the n-body problem where n for n 2 or less than 2 we can find general solution. We get the Keplerian orbits, right? What we get is if you take two masses m1 and m2, then you can write the equations of motion, and we can show that the motion of M2 around M1 has to be one of the conic sections. It can be a parabola, a parabola, an ellipse. Parabola, the ellipse is of interest because
Excuse me, sir, you are muted.
I got muted also. Yes. Okay, so this is the equation of relative motion. And to solve this, again, you use techniques such as uh, you take R1 by U and get it into another parameter and solve it. Okay, so let's not get into this as of now. What we know is to solve n-body problem where n is 3 or more, you cannot do it in a general, we don't have a general closed form solution, but you do have particular solutions, and the best way of handling these situation is use numerical solutions. So you use computers or take numerical techniques to do that. And now that when we are going to apply this n-body problem to astronomy, there are multiple situations where we we have systems which are n-body system, like we have star clusters, we have galaxies, we have uh, early universe. You can mimic the whole thing as this and do it. Okay, so yeah, so there are various for taking different initial conditions. You can get all kinds of different orbits, and you can do these using some software which is available, or you can write your own code. And the idea of this talk would be to help people interested in this so that we can work from three body to million body problem using different techniques or different software. So applications of N-body problem in astronomy, we have dynamics of the solar system, a very important question which pertains to our survival, whether our solar system is stable, will the planets move as they are always, or will someday they would collide with each other, or would Earth spiral toward closer to the sun or spiral away? On all these things, anything could be a disaster for survival. So we have dynamics of an evolution of star clusters. We can take these open clusters, globular clusters. We can look at dynamics of galaxies and the interactions. We can look at dynamics of clusters of galaxies and the large scale structure formation in the early universe. All these have applications, and cosmological simulations will be done by Sandeep. And I'll indicate in these two talks how to do for stellar systems, say star clusters or so on. So the approach is, the simplest approach is using this leapfrog algorithm. We know the position at a given time t. Suppose xi denotes the position and vi gives its velocity. You take a small time interval, and you update your next position. So your next next step would be xi plus delta t vi, right? And mind you, this is to be done with the y coordinate and also with the z coordinate. So you keep updating all the three x, y, and z coordinates, and you keep and then uh, this new xi becomes uh, the initial xi for the next step, and we can calculate the new vi from vi plus 1 by m delta t fi, right? Basically, fi by m is your acceleration. So acceleration acting for delta t times will give you the increase in velocity, and when you add that to the velocity, you get the next location. So this vi again would have the three components: vi, vxi, vzi, and v. Uh, Okay, so basically, what I'm trying to say is you have n particles whose coordinates, suppose, are given by the mass m1 has x1, y1, z1. Mass m2 has x2, y2, z2, and this way you have mn mass as xn, yn, zn. Yeah, all these are with respect to, say, some arbitrary origin, and you can find out, and the velocities will be, say, v of x1, v of y1, v of z1, right? Your v of x1 is basically x1 dot, yeah, x1 dot, y1 dot, z1 dot, and so on. So you keep updating your velocity. So this v actually has these three components. You have vxi and 1 by delta t into f into the xi component of so on, and these I again go from 1 to n. Right, so mind you, this the problem which started off by looking at our solar system and questioning whether it's stable or not, has led to a lot of mathematics. To start off with, Newton, he formalized calculus basically to study the solar system. And then it was further refined by various people like Lagrange, L'Hopital, Jacobi, and so on, all the way up to Kolmogorov of the 20th century, right? And in between, we had people like masters like Poincaré and others who looked into this three-body N-body problem at different stages, and a lot of mathematics like perturbation methods, yeah, calculus to start off with, perturbation methods, stability theory, topology, uh, calm theory, Kolmogorov, Arnold, Moser theory, chaos. All these are offshoots from studying the three-body or the N-body problem. And innumerable interesting techniques have come about to get rid of the singularities which come in this, and to techniques of solving differential equations or looking at the whole thing in a geometric way, right? So a lot of beautiful mathematics has come out of studying the N-body problem, and it has a lot of relevant applications in not just in astronomy, but in a variety of areas. So this doing N-body simulations is an art by itself, and it requires a lot of creativity. There's a lot of originality in it, uh, simplicity, and there's a lot of beauty in it, right? So, for example, to illustrate, if I am using computers like we did in the previous algorithm, the leapfrog one, uh, I use technique of finding how an object, a specific particle moves in time and getting the orbit. Uh, Much is dependent on the delta t which we take. The smaller the delta t we take, you get a smoother path, right? Otherwise, you get a jerky path. It would look something like that, right? And there can be issues when, though the particle may be going like this and coming, if you are taking a big time step, you would think it is going to collide with something lying somewhere, right? So obviously, the smaller the delta t, the better accuracy you get, but then it is at the expense of your computation time. So people have used very ingenious techniques of building on that. Uh, for example, you take a certain delta step, not extremely small, and you get the positions x naught, x1, x2, xn, and you use interpolation using one of the Newton's interpolation or Lagrange interpolation, find a polynomial which goes through these points, and then you can use these polynomials to find many more points where you can find its position, right? So you are getting their location, their position by fitting a proper polynomial which goes through a rough trajectory. Another thing which was done by Arseth and others were multiple time steps. So for objects, suppose you have a body which is very far from a given one, and if a body which is close to it moves by a small amount, the effect is pretty large. This attraction is in a certain direction, but when it moves even by a very small amount, the effect is tremendously large. It is pulling totally in a different direction. But if you take the same kind of time step for an object which is far, the difference is not really much, right? So they took multiple time step techniques where for objects which were close by, you you keep updating their positions and updating the effect of motion of nearby particles at smaller time intervals. But for objects which are further off, you update the variation in the on the force which is affecting its motion at larger time steps. So you use multiple time step techniques to do that, right? So and apart from that, like I said, there's creativity and so on. Very often you get some singularities in that. You see that when particles come menacingly close, the distance between them, computers run on discrete uh, mathematics. So beyond a certain level, you can set up an accuracy of a certain level, but beyond that, you may take it may that it may be treated. A computer may treat it as a zero and show that you are getting uh, uh, you are getting a zero in the denominator, and it's the computation stops and says not an integer, and the whole system stops. So to get rid of these issues too, there are various ingenious methods which come in. One of the simplest one is in the denominator. You have this Rij, and you add a very small parameter, and you are taking right. So this epsilon is 10 to the power of minus 4, or whatever, 1 into 10 to the power of minus 4, or whatever accuracy you want to take. But this forces the denominator never to become zero. So in some way we are attributing a finite size to these particles, so that no two particles the centers can coincide. This is called Plummer's softening. So this is one way of getting rid of handling this. Another one is there are certain regularization techniques which I already mentioned about. So you go from a certain domain of time to a fictitious time in such a way that when particles start getting too close to each other, they finally would the distance between them would become zero only this when this tau tends to infinity. This doesn't happen in the real time, but this happens in the fictitious time. And there's a regularization which is used in mathematics, which is called KS regularization, Konstantinov-Stiefel regularization, which has been very effectively and beautifully used by Arset in his Nbody code. So there is no limit to ingenuity and creativity in these simulations. And once you get into it, you start thinking on these lines, and you find better and efficient ways of handling this. So there are various algorithms, particle mesh, particle mesh, and so on, tree chord particle mesh, and symplectic methods, and so on. And for example, this particle, the naive method, is something like what we have discussed earlier. It accumulates forces by finding the force ij's between uh, any two particles, j, any particle j going from 1 to n, with respect to all the other n minus 1 particles, and integrates the equations of motions, which includes the accumulated force, and it updates the time counter and repeats for the next time step, right? So basically, you are updating the positions and velocities each time, and you are updating it and going up. But the downside of this is if your n number of particles goes up, then the time required to calculate the interactions goes by n squared. So these are very computation incentive ones, and they become inefficient for systems with uh, bodies more than million or so. And it requires tremendous amount of you require machines, teraflop machines, and so on. One way which was done was approaches to build a special machine which have multiple processors on it, And these machines are called grape or harp computers. These were specially designed to do the N-body simulations. So here we have Makino as a young man. Makino, Hart, and Arset. They went into making these. And basically, the hardware itself calculates the forces. There are many CPUs in it, and each one is calculating the force on individual components of that. And and these Hermite accelerator pipeline or hard machines or gravitational uh, uh, piping. These are these are special machines which have been made for N-body simulation, specifically for N-body simulation. One such earlier generation machine has been given to Indian Institute of Astrophysics, Bangalore, by the Japanese. And for a while it was being used. I don't know the present status, but yes, they do have one of these. For others who cannot afford these machines, they can think of making uh, clusters. You can use Beowulf clusters using Red Hat and rock and roll Red Hat and or so on. And you can use some old systems which are lying around and make a cluster of your own. And we had successfully done it in our institution, where you can take the disposed machines which people feel are old and useless, but you install and connect them and use them for these kind of things. So one is the solution using the hardware, but there are other ways where we can have other techniques like particle mesh. It breaks up the space into uniform mesh and places each particle. You keep breaking it into cells so that each particle is in an appropriate cell, and use discrete Fourier transforms to solve the partial differential equations. And this is a more efficient one where you use your computing time goes by m log m, right? And it is, but it is not good for studying very close encounters between particles, because if the particles are when they become very close, your mesh has to become extremely more refined and smaller, right? And also uncomfortable when you have non-uniform particle distribution. Okay, so though it gains in speed, but you have this downside. So there are various variations where you have particle mesh, which is a combination of both, and you have nested grid particle mesh and various things. There's another one where we have this top-down particle cell method, tree-based method, hierarchical competition, where you take the whole space where all the particles are situated and you break them into a grid, right? This actually, you should imagine it as a three-dimensional one. This is just a two-dimensional projection. But what you do is you have these particles uh, and you find a cube. You find a cube which in which all these particles are situated. Then bisect this cube, bisect this cube, and you get cells here. And if a certain cell has only one particle in it, then you can cell should have only one object. So we are not putting a uniform mesh like we did in the previous one. but we stop with a certain cell if the number of particles are less, and hence obviously you see the downside of the previous one is overcome here, because even if the distribution is not uniform, it's fine enough. And even in the regions where some particles come very close, you are just looking into that area and breaking up into smaller and smaller ones. Okay, and then what it does is for cells which are close to you, you take the individual force component here, but for those which are further off, for for those which are further off, you take the yeah. So you define a parameter d, and you are calculating potential by 1 by r. For regions which are far from you, you take the center of mass of that cell and you uh, for for a cell which is pretty far off, and we are looking at the yeah. So for a cell which is close by, you calculate the force due to these individual particles close to it. But if something is a cell is very far and this angle is defined, yeah, the distance is being defined by what is the angle the cell is subtending particles here. I take the center of mass of this, see what is the effect of all these particles in this, and I just calculate the force due to this one rather than right. So instead of having, say, suppose they are 30 particles here, we don't calculate the force on this particle due to all these 30 particles, but rather only the uh, that of the center of mass, which and your calculation speeds become very efficient. And again, you go by uh, or your computation goes by n log n rather than n square, right? But the downside is it requires a lot of oxygen, so much more powerful and uh, better. I have 10 minutes now. Yeah. So we have all such various methods, and well, you will not discuss them right now. But the idea was to bring to your notice that there are so many techniques by which you can enhance, you can improve your computational techniques. There are certain codes and toolboxes available which you can download and install on your systems. We will try to do this with some of them, maybe two of them, in our next session, which we'll be having day after tomorrow. And like we have Nemo, it's a stellar dynamical toolbox. You have Sky, Coyote, Nbody in Java. You have Nbody.c from parallel programming and C from trans for the transporters. We have Nbody 6 RSEDS code for star clusters. Uh, GalC, we have Gadget, Star Lab, and so on. So most probably I will in day after tomorrow's session we will look at say Nemo in Nbody 6. Nbody 6 is very good to deal with star clusters, right? And it's a very good code which is distributed by RSET, and you can freely download it and use it. And gadget will be covered by Sandeep. Then cosmological simulations and so on. So Sandeep will be handling these things. So applications, I'll run through some applications very fast. What are the things which probably we could work with this? When you look at these star clusters, there's something which is very common to most of them. We see that there is a brighter stars, there's an over density of massive stars which are sitting in the center, right? So the question is whether the star clusters are born this way, and or they evolve in a certain way. This phenomena is called this mass segregation. So when you look at star clusters, you see that low mass stars, though there are many low mass stars in a cluster, what we see that mostly when stars are born, they are born in groups, and when they are born, mostly the low mass stars are born. Most of them are low mass stars, and high mass stars are lesser, and they probably is some kind of a distribution where you see the massive stars sit at the center. So mass segregation is the systematic mass dependent distribution of stars as a function of distance from the center according to the masses, leading to the concentration in the cluster, or they are born that way. Is it primordial, right? So is the question is, does it happen that the clouds themselves are more denser in the central region, hence massive stars are formed in the center, hence you see these massive stars there? Or is it that these massive stars, they gravitate faster and they sink to the center? Like you collect a lot of potential while right. So is it the gravity which is gravitating them, pushing them to come together faster and leading to this, or whether they are born this way? So for this you can look at encounters in these clusters, and roughly you can uh, break up the force which is acting on an individual star as regular forces, irregular forces, and external forces. So external forces is you have a star cluster, and each star experiences a force due to the other stars, but also there can be an external force which is happening. For example, these clusters are in galaxies, so the galaxy itself gives a potential, the center of right. So this is the external force. So if you take these external forces, you assume it is zero or negligible, then you call this as a closed system. You are studying that star motion of an individual certain close to another star, then it experiences uh, 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 an irregular force, right? Which, right? So these regular forces is the attraction of the system as a whole, while irregular forces come due to chance encounters. When it comes close to another a star or so, it experiences can get ejected out. So innumerable things happen, which play a big role in how star clusters evolve in time. Right, so irregular forces dominate the system, then you treat them as the N-body problem. And if regular forces do it, then this hydrodynamical approach is a better suited one. Another interesting thing, just back of the envelope calculations show that if you have a star cluster and you have a giant molecular cloud or some perturbation which affects this, right? So a giant molecular cloud goes past, right? So I'm taking an impulsive approximation action. And what we see here is that we are looking at the change in the energy. So we have half mi vi. This is the change in the energy due to interaction, and vi is the original one. And when you open it up and you cancel out these terms, that in general, when there are many bodies, then the summation vi dot delta I, because these changes in velocities can be random, this statistically becomes zero. So the delta t, what we see is mi vi delta v vi square. Clusters, which can lead to escape of stars from the system. It can lead to dissolution of the star clusters or destruction of the star clusters, right? Another thing interesting in looking at star clusters is we can calculate the relaxation time. So once you have a star cluster which is formed in a certain location in the galaxy, after they have certain velocities at the time when they are born, and as time evolves, the whole system gets relaxed. So you can calculate this relaxation time, and we have these wonderful works by Beanie and Merrifield, which give you this in detail. And so what we can do is we can calculate the relaxation time, and you can see the age of the cluster. So if the age of the cluster is less than the relaxation time, then it can be an indicative of the primordial mass segregation, right? You see a cluster which shows mass segregation. It shows that there are more massive stars at the center, and its age is much less than the relaxation time for that cluster. Then we can infer, at least it is indicative, that this is a that this cluster was born with mass segregation in it, right? But when you simulations and other kind of works have shown various interesting things which show that the number of binaries, the initial binaries in it, or initially whether there is a mass segregation in the cluster, then this process of mass segregation becomes faster, right? It becomes much less than the computed relaxation time which that formula gives, right? So there are other things which we can get through these simulations, and that is the interest which you can look at. So you can look at clusters that different. You can use this RSET's Nbody code. It's a wonderful code where you can decide the uh, and what kind of distribution you want to start off with of clusters. You can have star formation in it. You can trigger on star formation in it. You can have various aspects in this and do very meaningful simulation. So you can do simulation by, yeah, you can trigger on and off external potential, right? The gravitational potential of the of our galaxy. So you can take these clusters of different sizes with different uh, uh, mass segregation, initial mass segregation. You can have different locations of the plane in the plane, and also keep the gravitational potential on, and see how these clusters evolve, and you can compare with the observations, right? So there are certain discussions of the simulation. The initial mass segregation affects the dynamical evolution of clusters. The presence of high mass stars with stellar evolution triggered expansion and early star dissolution for clusters, which fill the Roche lobe for the segregated clusters. For clusters which do not fill the Roche lobe, the early expansion does not make a significant difference in their cases. And the primordial binaries, they play an important role in the dynamical evolution of clusters. And presence of these primordial binaries can lead to in study of galaxies and see why these galaxies come in a variety of shapes and sizes. And for a very long time, people uh, thought that these galaxies were isolated high quality imaging and spectroscopic data. They did not have detailed theories of stellar evolution and nuclear synthesis. But one big blind spot which they had was they did not believe that gravity could work at such large scales, creating which are responsible for the formation of these can merge to form um, elliptical galaxies. Right prior to the works of Toomre and Toomre on with N-body simulations, people thought that it was the ellipticals which set into spirals, but uh, Toomre and Toomre showed that spirals can merge to form elliptical galaxies, and it could explain why you have all kinds of these weird galaxies. So these tails are formed basically because of tidal interactions, and as things see, I'm stopping the simulation at this stage. So there are these stars which are gaining energy and being thrown off, and they are gaining energy at the expense of the gravitational potential energy, which is lost here, and the centers are merging to form one system. And right, so uh, a simulation, these N-body simulations give you a deeper insight into not just in star clusters and how they evolve in time, but also in galaxies and with this. And yeah, so there are a variety of things which can be done. And with this, uh, I'll stop for a quick one or two questions. And thank you for listening. Okay, so if we do not have questions, or if you have questions, we can interact on the forum. And the first session, we had some initial discussion on our web page and other things. So we have lost time, and let's cover up by going to the next speaker. So if yeah, Sushan Konar is here. Professor Sushan Konar will be giving the next talk. Sushan, I'm making you. Sushan is.
Yeah. So hello, good morning. Morning. Morning, Priya and Nazam.
Hi, hi, hi. So we have our next talk by Sushan, and Sushan has is going to be giving 2 talks, once today and once on Monday. And she'll be talking about the glitches and the with us in astronomy from archival data. I've already worked with her and I've heard her. So we're looking forward to Sushan's talk. Yeah, thank you. Yeah, Sushan, you could take over.
Okay, I will first I'll share my screen and then I will put it on right. Am I visible and audible?
Yes, ma'am.
Okay. So, very good morning to all the participants. I would start by thanking Professor Nazam Hasan and Professor Priya Hasan for bringing this IAU OAD projects again and again. Last year we had one project, and this is kind of a continuation to that. So thanks, Priya and Nazam. And I would also like to thank the student participants who are joining from all over the country, and some are even from different countries, I understand, to listen to these talks and take part in the research program that we would hopefully undertake. And I see some of the old ones who had worked on the previous project, and they have also registered for this particular set of workshops. So welcome you all. And as Professor Hassan has mentioned before, that this is some sort of a continuation from the previous set of lectures and the follow-up projects. So I would urge the participants who did not attend the first set of the 2020 sessions to go and listen to the lectures which are there on the YouTube, I believe. And you may also like to listen to the project presentations that the student gave at the end of that activity. So then you would get a very good idea of what we did. And because this time we are doing it in a different fashion, and this time we were starting with at least this set of lectures that I would be giving is only 2. So I would skip a lot of introductory material and jump into the essentials which we would require for the projects that I have in mind. So therefore, of course, you are most welcome to post your questions in the forum, as Professor Hassan has mentioned. And we would try to answer all the queries and questions you may have. But I strongly urge you to go and listen to those previous lectures and the project presentations. So before we go into jump into the activity, let me remind you that the history of astrophysics is where we have perfected timekeeping. And it is actually timekeeping which we would be involved with. We would not really do actual timekeeping, but some properties of radio pulsars, that is the neutron stars, that we know about is simply because of our perfect timekeeping, and those are the properties we would be trying to deal with. So please remember that it's the timekeeping which is very important in astrophysics. So now, usually I talk about the resources at the end of the lectures. I thought this time it will be easier. Sometimes it helps to have the resources up front. So here are a few books that would be relevant for the kind of projects that you have in mind for this activity. And no, this is not a comprehensive list on the physics of neutron physics or astrophysics of neutron stars, but this will give you a quick introduction to, when I say quick, it does not mean it's very simple. Many of the books are fairly advanced, but a quick introduction to that particular aspect of neutron stars which we would be dealing with. Not everything. Neutron stars, please remember, it's a very complex and complicated physical system, and try as we might, it's very difficult for any one of us to understand every aspect of that object. So this set of books will give you a quick introduction to neutron stars as radio pulsars. And here are some of the resource sites that we would be using. In particular, I urge all of you to go and play with the resources that are there in the ATNF catalog, and there you would find huge number of parameters, measurable parameters, and some are derived parameters which have been compiled there. And you not only get tabulated results for various searches, you can even get plots which you can generate for your own curiosity and try to see how the objects behave. So actually, I believe playing with the pulsar catalog at ATNF is a very useful sort of toy, toy to play with, and to get a very quick view of the field, the current status of the field. And I would be showing some of the plots that has been generated by this catalog, and you will see that how helpful these plots are. So I urge all of you to go and play with this catalog. And of course, then there is this Jodelbank catalog of glitching pulsars. Now, what are glitches I would talk about on Sunday. And so this is one extremely useful catalog. And here is another catalog which is maintained by me. This is a catalog of nulling pulsars, and this catalog will give a list of the nulling pulsars with some of the parameters, and we would talk about the nulling pulsars today itself. So I said the name of the lectures is Radio Pulsars, Blips and Hiccups. So now the previous set of lectures that we had last year was called Astrophysics of Neutron Stars. So obviously now from neutron stars we have come to a small subset. It's not small, this is the largest subset of neutron stars that we know about, but nevertheless all radio pulsars are neutron stars, but all neutron stars that you know about are radio pulsars. So radio pulsars is a subset of neutron stars, and what we'll do is we'll learn about radio pulsars, then we'd learn about the nulls of radio pulsars that we see, and we have to understand the interiors of neutron stars in order to understand the phenomenon of glitches. So these last two sections should be dealt with on Sunday, and today we will deal with the first two. So here is the famous magnetic field and spin period diagram of all the neutron stars. Now, many of you may have seen this particular diagram itself, or at least some other version, some other rendering made by other people of this plot, which sort of shows all the neutron stars for which we have some measure of both the spin period and the magnetic field. And you see that these objects and these pink objects here, these are in accreting systems, and about which we would not talk in this set of lectures, and we would keep them away for various reasons. And so if I try to compare this with a plot that we obtained from this ATNF catalog. ATNF catalog does not have these accreting objects. What do we have? We have this kind of plot. This is the earlier one, and this is a plot which has been obtained from the ATNF catalog. You will see that there, of course, they are the same, except for the fact that these objects have disappeared. We don't need them. Now, in this plot, the different colors and different symbols stand for different observational classes of neutron stars, radio pulsars, magnetars, etc., etc. I have not mentioned any of them, so don't worry about them. But in this plot, the different colors refer to, as you will see from the legends here, that the green objects are the pulsars, the neutron stars with binaries, which have a binary component. And here also you will see that the ones which are drawn in open circles, they are in binaries. So these are the binary objects. And here the red objects, the red triangles, are actually high energy pulsars. So what do we mean by high energy pulsar? High energy pulsars are those which are seen in higher frequency of emission. When we talk about radio pulsars, we mean that we are seeing the emission in radio band. And for these objects, we predominantly see them in the higher energy, optical, X-ray, gamma rays, and so on. And some of these high energy pulsars, which are seen predominantly in higher band, they may or may not have radio counterparts. So therefore, now of course, this particular plot doesn't have that information, but here you have that information, and you immediately see that this set of objects which are marked as magnetars here, the ones which have very strong magnetic field, they seem, all of them seem to be a very high energy objects. And some of the millisecond pulsars, why millisecond? Because their spin period is very small, in the range of the millisecond. Some of those are also the high energy pulsars. So you will see that the observational classification, when we see them, we classify them depending on various properties. So many, in particular here, we have only talked about the nature, and we have not talked about any other property here. The moment you plot the properties, you see that the observational classes are showing difference. So this is what, of course, there are many other differences when you go from one observational class to another, but this is one illustration of that. So now what we do is, now let's change the name of the game. So what you do is, this is the plot you have seen in the previous slide. This is magnetic field, and this is spin period, and these are all the object. Now I would start calling them radio pulsars, even though you know that these are all these are not radio pulsars. So what I will I would, of course, I would not call them radio pulsars as yet. what I would say is that these are the objects for which magnetic field has been derived. Magnetic field has not been measured. Uh, in some neutron star systems, we directly measure the magnetic field from cyclotron lines, etc. But these are the objects for which magnetic field is a derived quantity, assuming that the spin down rate of pulsar, neutron star, is because of the dipolar radiation, and we assume a magnetic dipole field, and we using that model we derive the value for magnetic field. But we are not measuring the magnetic field directly. What we are doing is we are assuming a model and deriving that quantity. So then what do we measure? We measure spin period, yes, and we measure the spin period derivative. These objects are slowing down, so we can measure spin period derivatives. Now I want you to look at this plot very carefully. Now we have this spin period axis on the x-axis, and you see that this is going from some millisecond to some tenths of seconds. Now you look at the derivative, the p dot, the value which is second by second, it's a dimensionless quantity, and it is running from about 10 minus 9 to 10 to the power minus 22. So now you see how stable the spin periods of these objects are, and of the majority of the objects which are here in this blue island, there the spin period derivative is about from 10 to the power minus 12 to 10 to the power minus 16. So this is extremely small, and therefore the spin period is very stable. So pulsars are supposed to be the most stable clock in the universe. If you come to this, close to 10 to the power minus 21, they are even more stable than the standard atomic clocks that we use terrestrially. But that is a different story altogether. But this is the quantity we are actually measuring. Now, the moment we turn this plot around and plot, instead of P and B, we start plotting P and P dot, we see that the nature of the plot changes not very significantly, not very dramatically, but a little. And from here, we actually get something very interesting. You see, here also we thought that, as if, I'm sorry, this particular island seemed to be disjoint from these red points and this set of points. They look like, they are separate, they are different. We know observationally they are different, but when we are first observing a set of neutron stars, a set of pulsars, how do we know they are different? As they keep, as the numbers increase, as we keep collecting more and more objects, we see that they do not fit the expected pattern. They are not on the fringes of this huge island, but they are going far and far away, and these things, they seem to be going upwards. They do not seem to be really fitting inside this island. Now we come to this picture, and now the disjointedness of this set of objects and this set of objects from this main island seem to be even more apparent. And we know that they are very different, because these objects, which we usually call millisecond pulsars, the specific precise definition as of today is that spin period less than about 20 milliseconds is called a millisecond pulsars. And we know that these pulsars are actually recycled pulsars. They had a binary companion, and there were some processes going on, and because of that, both their magnetic field became smaller and the spin period become smaller. So the evolution of these objects different from these objects. So maybe we should not put them in the same bin. They are apples and oranges. They shouldn't be together. And here are these objects which we also know seem to be different simply because they have different very large magnetic fields. No, because all these objects here and also these objects here seem to be powered by the spin down. So the rotational, because they're spinning down, the rotational energy is decreasing, because remember rotational energy is I omega dot square, where omega dot is your spin frequency derivative. So spin is so you have the energy going down, and that energy is going out as a radiation. So this pulsar is basically shining because of the spin down. Now it appears that for these objects the spin down energy is not enough, and we suspect that the energy that is basically powering these objects is the decay of the huge magnetic field. So the nature is different. The nature is completely different. And so therefore, what we'll do next is we will put these different beasts away. We don't want to consider them at the moment. So we go forward. And so from here, we have taken away all these different fellows, and we have also taken away all the millisecond pulsars. So what do we have left here? We have this huge island, but we see there's still some scattered points which do not seem to be fitting into this group. So what we do is we also take out the binary objects. You see, these are all mostly green objects, and they're all in binary. So let's check them out. So we have now thrown out the green ones. Also, we have a few scattered points there, but now we have sort of a coherent group of objects, which we would call the rotational powered pulsars. But because, as I have already explained to you, the energy is coming from the rotation, the spinning down of these pulsars, and these are isolated because we have thrown out all the binary fellows. So now what are we going to do about these objects? What's so interesting about them? Let's go and see. So the discovery. So let's start from the beginning. So in 1965, please remember the idea of neutron stars is very, very old. The theoretical idea was came about 30 years before the neutron stars were actually discovered. So you should go and read about this extremely interesting story involving Lev Landau and other people. Anyway, so in 1965, Anthony Hewish, who will play a very important role in the next slide and next year, and Samuel Okoye observed an unusual source of high radio brightness temperature. What is radio brightness temperature? We'll talk about in a moment. In the Crab Nebula. You know about Crab Nebula and the neutron star sitting there, the Crab pulsar, the famous Crab pulsar, which is basically a laboratory for all the neutron star characteristics you can think about. So people are continuously observing the Crab pulsar and trying to understand various features that are related to the physics of neutron stars. So this Crab pulsar was detected in 1968 before, after pulsars, what pulsars was established. But before that, this is 1965, pulsars have not been discovered yet, and they see an unusual source of high radio brightness temperature. This is the Crab pulsar, which will be discovered a few years later. Sorry. Right, 1967. Jocelyn Bale, PhD student of Anthony Hewish, they were looking at interplanetary scintillations They were not looking for pulsars, of course, they didn't know. And this was a completely serendipitous discovery, a momentous serendipitous discovery. They were looking for interplanetary scintillations, and then they detect regular radio pulses from this object, which they named CP1919, which was named by the position in the sky. And later, this became the famous pulsar known as the J1921 plus 2153. People who are a little familiar with neutron star or pulsar astrophysics know that they are named by the RA and deck positions, and this is how a pulsar is typically named. So here are the regular radio pulses that this is shown in inverse, of course. These are the pulses. Here it is shown as dips. So, so this object with a period of 1.33 second is keeping sidereal time. So, which means that this is something which is coming from the sky, and this was the first detection of a radio pulsars. So, radio pulsars. So now we are coming to understand the name of it. We're getting regular pulses. So it's a pulsar. It's not a Bajaj pulsar. If you go search for pulsar in the internet, you get this huge motorcycles which are Bajaj pulsar, but no, this is neutron star pulsar, and they were seen in radio, so therefore they are radio pulsars. So this is a typical plot for how the pulses arrive, and these are observed through radio telescopes like the GMRT that we have 80 kilometers from Pune, maintained by National Center for Radio Astrophysics, which is a center of Tata Institute of Fundamental Research. So such radio telescopes detect radio pulsars. Though please remember the Cambridge telescope, which detected the first pulsar, was not of this type. It was of a different type. Nevertheless, it was a radio telescope, so through which the first pulsar was detected. So now, please. So before we go into the problem of the radio pulsars in particular, let me quickly try to impress upon you the importance of the kind of problems we are trying to do. So you may think that neutron stars rotating in the sky, very esoteric, and this lady is interested in it, but why should I look at this, right? Okay, so I'm sure you have seen this picture in many places. This is the standard picture taken down from the internet, and what it shows you is that this is the atmospheric opacity. What is opacity? It's the through which what opacity means. So it's the opacity to the electromagnetic waves coming from the sky. So it writes down the wavelength of various the electromagnetic waves and shows which are the frequency bands or the wavelength bands where the sky is opaque and where the sky is transparent. Wherever the sky is transparent, we can do ground-based observations. Wherever the sky is opaque, we have to fly a satellite up there and do the observation from there, because the atmosphere is opaque. So we cannot do ground-based observation. And what you notice here is, of course, this is our visible band. If this band wasn't transparent, we wouldn't have been seeing the sky at all. So that is transparent. And this huge band here, there are little bands here and there which are transparent, but mostly the atmosphere is opaque to majority of the electromagnetic frequencies, except for this huge band, which is the radio band. So therefore, we can do very good radio astronomy from the ground, even though you know that nowadays it's becoming more and more difficult because of the interference from all the man-made machines, all our mobiles and our digital TVs and even our vehicles and planes flying overhead, or the satellites or weather communication satellite, or Elon Musk's toys. All of this is killing our opportunity to do radio astronomy from ground, but still now we can do it. And so therefore radio astronomy is one branch of astronomy, observational astronomy, which is very easily, which has been traditionally been something that you can do easily from the ground. And we have an advantage in radio astronomy, because for any telescope, you may know that the resolution in the sky, the smallest part in the sky that we can clearly see, is proportional to the wavelength divided by the diameter of the telescope. So therefore, when we can resolve very small angles if we make larger and larger dishes. Now, you would say that why is that not possible for, let us say, optical or for X-ray frequencies? Simply because you cannot make such huge, let us say, huge optical dishes, which would be stable, and you can have very fine resolution there. For radio telescopes, it's possible, it's doable, and we have been doing this. For example, the latest single dish telescope, which has been built in China, which is called FAST, 500-meter aperture spherical telescope. So the diameter of the telescope, which is actually in a large, huge crater kind of region, it's 500 meter. So they have a very fine, excuse me, resolution. But if we cannot make such huge single dish telescope, in radio astronomy, we have the advantage of doing radio interferometry. Instead of one single telescope, we can combine a number of telescopes, an array of telescopes, and the distance, the largest distance between two such elements in an array will be my effective radius of the array, and therefore I can again have very, very fine resolution. This is the principle on which a telescope like GMRT works. And here we have the distance is the diameter of a single dish is 45 meter, but the length, the distance between two farthest such single antennas, these are one single antenna with a 45 meter diameter, but if you take two antennas which are farthest in the GMRT array, that is 25 kilometers. So it gives me a huge diameter, effective diameter of the telescope. And this telescope works at a frequency of 150 to 1500 megahertz, and the resolution ranges from 2 arc seconds to 20 arc seconds. So you see that we have achieved something really fine, a very fine resolution. And because we have a number of dishes, so the collecting area is large. Those of you who do photography, you know that if you are doing a very faint light photography, so you have to keep the aperture open for a long time and for a lot of light to collect so that you can have a good picture. So it's similar. And here what we are doing is we are having a lot of collecting areas, lot of dishes, and we are collecting a lot more photons, and so our sensitivity goes up with the area of the telescope. But we are doing even better. We're going to do even better when the square kilometer array comes up in South Africa and Australia. And of course, we had to go far away from civilization to be away from all these man-made machines which would interfere with the radio signals. And the construction is to begin soon. And we hope to have this huge, the monstrous telescope active and collecting data by the middle of this decade. And this works in a huge range of frequency, and the resolution is going to be 50 times smaller than what we have achieved in geometry. So this is where the future of astrophysics is going, and we have this enormous possibility of doing neutron star physics with this. Actually, one of the major major thrust area of science for SKA is neutron star astrophysics. So therefore, those of you who want to go into astronomy for your future career, you must know that this is something one can really do with a meaningful sort of future in mind. In other words, that exciting things are going to happen in this field. It's not some old lady is excited about this exotic object. Why should I do it? People are excited, and extremely good data is going to come. New frontiers for this field would open up, and therefore maybe we should prepare ourselves. I mean, people like you should prepare yourselves to take that opportunity. So, and I'm sure you have heard about the multi-messenger astronomy, because an object doesn't care whether we have a radio telescope or an optical telescope or whatever. Okay, physical object in the sky has certain physical processes going on. So maybe the same process gives rise to radio emission, and the same process gives rise to X-ray emission. And we would like to understand that process in its totality, and therefore would like to observe via radio telescope and some other high energy telescope. And therefore, in that context, AstroSat, India's own satellite doing astronomy, is very useful. It is looking at the sky in X-ray, and there already are several programs in place which are looking at neutron stars simultaneously with GMRT at radio bands, and with AstroSat at X-ray bands, and they are finding very exciting new physics understanding from such data. So you must remember that even though most of the neutron stars, as I have as was apparent from the pictures that we are seeing, that most of these objects are visible to us as radio pulsars, but many of them are visible in high energy, and there are other kinds of neutron stars which are not radio pulsars, that is the accreting systems and so on, which are also mainly visible in high energy bands. So we can do good multi-messenger astronomy with all these instruments. And of course, these days, one must remember that we have this other window of astronomy which has opened up for us, that is the gravitational wave spectrum. So we have the detectors in the ground-based detectors, which are LIGO and Virgo, and some space-based detectors are coming up in future. And what is happening on the ground at this point of time is we are having ground-based gravitational observatory being one such observatory being built in India. So this would be the Indian arm of the LIGO. So they have a collaboration with LIGO. So gravitational wave astronomy is another branch from which we are getting exciting new understanding about the universe. And on the one hand, we can study neutron stars through gravitational waves. And you must know about the neutron star merger event, which was detected by LIGO a few years ago. And this was then followed up by electromagnetic telescopes, in other words, radio telescope, optical telescope, high energy telescopes, and so on. And the process was understood, what happens when two neutron stars merge and so on. On the other hand, we can use the extremely I'm sorry, fine precision of neutron star spin periods. You have seen from the plot that the p dot goes down to 10 to the power minus 21 second by second. So we can use an array of such neutron stars in the sky to make an array of make an interferometer in the sky, which is called a pulsar timing array. Using those, we can detect gravitational waves in the sky, because gravitational waves, when they move through the move through a region of space, it modifies the space time, and that uh, can be found, that can be calculated from the time of arrival of the radio pulsar signals, because they are very precise. The timing is very, very precise. So any small change can be calculated, and from there we can detect gravitational waves from there. So neutron stars are also intimately related to this new way of doing astronomy. So that's why before plunging into the problem, I wanted to give you this perspective of why one should be worrying about neutron stars. So now, as we have seen that we have discovered in 1967, the first radio pulsar was discovered. But the pulse that we found at that point of time, it seems that different neutron stars, different radio pulsars come with different kind of pulse shape. There is huge variation in pulse shapes. As you can see, this looks like it looks more like a pillar, whereas this looks more like a very sharp Gaussian, and so on. And they also have very different shape at different energies. And I must impress upon you about the fact that please remember, the radio pulsars, the rotation power pulsars, we seem to be interchangeably use these names, the rotation powered pulsars and the radio pulsars. Please remember that the rotation powered pulsars, they may or may not have radio emission. Some of them do not have radio emission. We do not observe the radio emission. It's better to say in that fashion. Emit in a huge band of energy. So they have emission in optical, in X-ray, in gamma ray, the same object. The same object has emission in radio and optical, to X-ray, to gamma ray. And the amount of energy that comes in the radio band is but a small fraction of the total energy emitted. So when we say radio pulsar, we have to remember that the amount of energy that we are getting in the radio band is only a small fraction. So rest of the energy is going into the other bands. So now for many pulsars, we have been able to see them in various frequency bands, not only in radio. Of course, for many pulsars, we have not seen them in other frequency bands, but fortunately for some, we have seen them in other frequency bands. And here are a few radio pulsars, few pulsars seen in different energy bands. Now I have talked about crab, the most famous pulsar. Here is another one, the Vela pulsar, and you see that the pulse shapes are very different in different energy bands. So this is in gamma ray, X-ray, optical, radio, same pulsar, but the pulse shapes are very, very different. And this is Jiminga. This is another famous pulsar, which was the first pulsar to be detected in gamma rays. And after much search, this Jiminga has not been seen in radio. Does it mean that it does not have any emission in radio? It probably has emission in radio. It's possible that we are not viewing the radio emission at an angle that which is not, the radio emission is not coming towards us, it's not beamed towards us. And so therefore you see that different pulsars may have different kind of pulse shapes at different energies. So the model of radio pulsars, which you need to understand before we go into before we talk about the properties. So in 1964, this is before the radio pulsars, the pulsars were detected. Low-Volcher from magnetic flux conservation estimated that the magnetic field of a neutron star would be around 10 to the power 14 to 10 to the power 16 Gauss. Now, please remember that the idea of neutron star, the theoretical idea of neutron stars, has been around for 30 years before they were discovered. So people were thinking about them, and Low-Volcher has this suggestion, magnetic flux conservation at the time of the supernova explosion, in which a neutron star is formed from a reasonably massive main sequence star. Now, in 1967-68, Franco Pacini indicated the likelihood of strong radiation from rotating magnetic neutron stars, which may power supernova remnants like the Crab Nebula. Okay, so he was talking about a neutron star, a pulsar, powering the Crab Nebula, which it does. And very interestingly, when Franco Pacini was developing his theory, he was sitting few rooms down the same corridor in Cambridge, where Anthony Hughes with his students was discovering the pulsar. They didn't talk about this till much later. So in 1968-69, around the same time, Thomas Gold develops a model, similar model to Franco Pacini, to explain the radiation from CP 1919. That's the first pulsar. Now the pulsar has been discovered, paper has been published in Nature, and so everybody is very excited. 1969, the same time, Radhakrishnan, V. Radhakrishnan and Cook, Gunn and Ostreicher, and Goldreich and Julier first made the model for a radio pulsar. How is it that we get this regular pulses? Now, before we go into this model, please remember we were talking about brightness temperature. Okay, so before the model, we have to collect all that we know about radio pulsars. So the brightness temperature of an emitting region is, we get the intensity of some emission that we are getting from the sky, and we blindly assume that it is coming from a black body process, a black body object, and we try to equate this intensity to the Planck function. You all know about the Planck function, the black body radiation function, of at the same frequency. So now we have an estimate for the temperature of the black body that is there in the sky. Now, in the Rayleigh-Jeans regime of the black body, Rayleigh-Jeans approximation regime of the black body function, the Planck function, you have a formula like that, where the intensity is roughly proportional to the temperature of the black body. Now, what happens for the pulsar radiation if you blindly do this exercise? What you find is that the black body temperature, the temperature of the body in the sky, which is giving off this emission, is 10 to the power 23 to 10 to the power 26 Kelvin, which is totally absurd. Okay. Now, this is an unfeasibly high energy to give to the particles that must be the constituents of that body. And if at all be possible, then the energy should have come at much higher frequency, because if the particle energies are that high, the radiation would have been at a much higher frequency compared to radio. So therefore, the pulsar emission cannot be black body radiation. So this is one very important input that went into making the pulsar model. So it was understood that it is actually coming because this object has a very strong magnetic field, assumed to be dipole. Initially, it was assumed to be dipole. Later on, we now know that the magnetic field is not a pure dipole. It must have higher multipolar components. But to the first approximation, it is a dipole field. So we can estimate the stellar magnetic moment like this. If BP is the surface dipolar field, and if R is the radius of the star, then M is the stellar magnetic moment. From there, you can calculate if this magnet is rotating at an angle, it is making an angle to the rotation axis of the star. So therefore, you have, forget about the star, forget about anything else, think of a bar magnet which is rotating about an axis, making an angle to that axis. So therefore, you have a magnet which is rotating about an axis, and therefore it is going to radiate. So that is the radiation that we are getting from a pulsar, and this radiation is coming at the expense of the rotational energy of the star, and therefore it is slowing down. So what we have is the radiative energy. If you take that magnetic moment and do your electromagnetic theory calculations, you get a formula like this, where this alpha is the angle between the rotational axis and the magnetic field axis, and omega is the rotational frequency. And if you assume it's to be a dipolar field, this is what you get. So therefore, the magnetic field, as you remember, I said this is a derived quantity. Magnetic field under this model is proportional to the spin period multiplied the spin period derivative to the power half. The square root of spin period multiplied by spin period derivative. So this is the root of the estimation of the dipolar magnetic field from a measurement of spin period and spin period derivative. Please remember, there are a lot of assumptions going into it. Later on, people have been trying to revisit these assumptions, and there are a lot of problems with that. These are some of the burning questions and the areas of research even today. But this is the first, let us say, the first approximate model people started working with, and this is still the model that most of us are using for making progress. And from here, we can also make an estimate for the characteristic age of the pulsars, assuming the initial spin period to be very, very small. So this is a summary of the radio pulsar model. So here is the neutron star, and it has a dipolar magnetic field which is at an angle to the rotation axis. So, and as you have already seen, the spin period ranges from about a millisecond to about tens of seconds. The surface magnetic field goes from 10 to the power 8 to about 10 to the power 15 Gauss, and all this is obtained using the dipolar model. So what we have here is the radiation is basically the synchrotron radiation, the Compton scattering of particles, and radio radiation mainly comes from the curvature radiation, particles moving in the curved magnetic field. So of course there are other processes which can slow down the neutron star, the pulsar, and gravitational radiation is one such. Of course, if you consider the neutron star to be as a rotating mass quadrupole moment. So for gravitational radiation, you must have a mass quadrupole moment, which will give rise to the gravitational radiation. People who are not familiar with this part may skip this. Only remember that the actual slowdown is a combination of electromagnetic radiation and gravitational radiation, and for radio pulsars, the component of gravitational radiation is likely to be very small, unless it has some strong asymmetric features on the surface. And some of us have shown a few years ago that for isolated radio pulsar, the effect of gravitational radiation would be really small. So now we finally come to the important topic for today. I said we'll talk about nulls and glitch, and today it's the null, the blips, that is. So the nulls of the radio pulsars, what are they? Okay, so as I have already said that the timing is very important, and the pulsars, very precise timing. The fractional stability of millisecond pulsars, those objects with p dot 10 to the power minus 21, are very stable, even better compared to atomic clocks. And I have also talked about the pulsar timing arrays, and the good news is that we have two major international pulsar timing arrays. What do? They select a set of millisecond pulsars, objects with very small spin period and really small p dot, so very stable clocks, and they select some of them in the sky, the suitable ones in the sky, and keep monitoring them all the time and look for any change in the arrival time of the pulse. So these pulses are very precise. They come after a very definite time interval, and if there is any change in that time interval, then one goes and looks for possible signs of gravitational wave. So now there is this international pulsar timing array and another European pulsar timing array, and we have our own Indian pulsar timing array, which uses a set of pulsars and continuously monitor them through GMRT and ORT, that is the OT radio telescope. Both are maintained by National Center for Radio Astronomy, that's NCRA. And only recently, a few weeks ago, this Indian pulsar timing array has now officially become part of the International Pulsar Timing Array through a lot of hard and dedicated work by a number of radio pulsar scientists in India, and very sort of heartening news that so in particular colleagues from NCRA and as well as Institute of Mathematical Sciences Chennai and main TIFR in Mumbai, so they have all been working really hard to get this going, and now they're part of the IPTA. So this is one exciting area of work that is going on. So so as I said, the pulsar arrival time of a pulsar. So here is a neutron star, here is a radio beam. Please remember I I'm not sure if I had mentioned that. Here. So here is a beam of radiation which comes to us, and because this is rotating, this beam of radiation, this is rotating. So only when this beam cuts our line of sight, we see it. So this cuts our line of sight once every period, and therefore we get a pulse of radiation, and that is the reason behind getting regular pulses from a pulsar. I'm sorry, I skipped this part. And I'm again reminding those people who did not attend the first set of lectures in 2020, please go back and listen to these lectures, because there we talked about this in much more detail. Okay, so this radio beam is coming to the telescope, and this receiver receives this, and various processes happen which I would not go into, and it defines a mean pulse profile. So all pulses do not look exactly the same, but you define a mean pulse profile, and with respect to that, one defines a TOA, the time of arrival, the expected time of arrival, because we have calculated the spin period and the spin period derivative, that's the slow down rate, very precisely. So therefore we can define a very precise time of arrival. And of course you would now not go into the detail of this, and there are various processes, various factors which give rise to a delay in the arrival of the pulse, because of the movement of the solar system, because of the movement of the earth on the orbit, and various other factors. We would not go into that either at this point of time. And then finally we do all that, and what we have are very regular radio pulses. Okay. Now there are some objects for which some of the pulses disappear. We are looking at them, we are seriously, constantly monitoring them, but we see that some of the pulses are not there. These are called the nulling pulses. For some, most of the pulses are not there, only few appear. These are called extreme cases of nulling. These are called intermittent pulsar. They are only pulsating intermittently. Most of the time they are sleeping, doing something else. And then we also have these objects called RRATs, which are sporadical emitters. We do not see a nice pulse train at any point of time. Now, I must mention here that these RRATs had been thought as really extreme cases of nulling. They mostly null, they mostly sleep, and once in a while wake up and has one or two pulses and then go back to sleep. Now it appears that this is very interesting. One of the projects that we undertook as part of this IAU OAD activity last year, one of the groups found that various physical parameters, if you compare the various physical parameters of the nulling pulsars, the regular kind of nulling, and the RRATs, they do not seem to match. So the populations are different. So the suggestion that the RRATs are probably extreme cases of nulling may not hold. We are still working on that, but the preliminary suggestions are very exciting. So the nulling behavior, so these are pulses, the regular pulses coming from, so these black dots are one pulse coming at a time. So this is with time, and this is the pulse phase. So you have the main pulse coming here, the other times there is nothing. Okay. So now you see that for this object, there are some gaps here, some gaps here, some gaps here. Now this is one nulling pulsar. On the other hand, this fellow has huge gap here, little bit of pulses, another huge gap, and so on. And you see that, for example, this fellow, there's only one little window in which it is the pulses are coming, and then it's mostly absent. I'm sorry. So you see that these are all nulling pulsars, but the pattern of nulling can be very, very different from one pulsar to another. And these are associated with various, it's not only nulling, so various other processes are seen. What are these processes? Now, as I have shown you in the beginning, that the pulse, the nature of the pulse is very different from pulsar to pulsar. Now, many pulsars do not have one single peak, but they may have smaller peaks called subpulses, small intensity peaks. And these pulses seem to drift in the phase time, in the sense that you have one whole period. So the pulse arrives at a particular point within that period, and sometimes the pulse seem to be drifting within the period from one part to another, and such behavior is also associated with the nulling behavior. And it also changes mode. What do we mean by that? For example, here is one particular pulsar. Now, it goes through different modes. So in here, okay, so radio and X-ray brightness changes nature. See, for example, here, this is the radio pulse. Radio pulse is very strong, and X-ray pulse is almost not there. It looks like noise. On the other hand, here, the radio pulse is weak, and the X-ray pulse is very, very strong. Okay, so such mode changes from the main intensity, the luminosity, the energy emission. It moves from one frequency to another. That is called mode changing. And also, for nulling, when the nulling happens, that for that, the nature of the pulse shape may change. So, for example, for this particular pulsar, the pulse shape can change from this to that, or this to that, or this to that. So you see that these particular pulsars have different nulling behavior. As you can see that here, there is only a small nulling window. This one has a bigger nulling window. But you see that the nature of the pulse is also changing. So something very interesting happening, and we really do not yet have the entire picture. What is happening and why it is happening. So in astrophysics, like in every science, the main question is why. Anything that happens, why it is happening. We really do not have much idea about why this is happening. All we know is null is abrupt cessation of pulse emission. It is associating with drifting of subpulses. It associated with mode changes. It associated with switching emission frequencies. And it is also associated with change in P dot. You remember P dot? It's very important. That is a very important measurable quantity. It has been seen in some pulsars, not all nulling pulsars, that the P dot measured at the time of nulling and P dot measured at the time when there are regular pulses changes. Now, there are some explanations, but had that explanation been correct, then we would have seen this phenomenon in every nulling pulsars. We do not see them. So therefore, I'm not talking about that explanation at the moment. So this is characteristics which we'll talk about later. The summary of population characteristics. We would again not talk about that. I want to show you this. So this is all nulling pulsars plotted in spin period versus magnetic field diagram, the BP diagram. And you see that these are called death lines. You see that there are all these pulsars and you do not have any pulsars in this region. So there are theories why that happens. So particular combination, beyond a particular combination of magnetic field and spin period, the emission mechanism processes, those processes responsible for emission, those processes do not, cannot continue, and therefore we do not have any emission from these objects. I mean, neutron stars exist in these regions, of course, but we do not see them as pulsars. So this is called the pulsar graveyard. And you see that, and all these different death lines are for different models, in different theoretical models. What you see is that it seems that this particular region in which all these nulling pulsars are concentrated. We have a geometry project ongoing. We have taken the data, we are analyzing now, and we're getting very exciting results from there to actually trying to see that is it really true that there are certain regions in the magnetic field spin period plane in which the nulling pulsars are confined. That would tell us something about the intrinsic nature of the nulling pulsars. Okay. Now, subsequent, this was done in 2019. A subsequent work was done by Sheikh and McDonald this year.
Sorry to interrupt. Sorry to interrupt.
I'm finishing in a minute. I know.
I'm very sorry. I'm sorry.
Yeah, no. I know I have sort of gone beyond.
Maybe it's okay. You're in the mood. It's fine. No problem.
No, this is the last slide.
Okay.
So here you see they have plotted the nulling pulsars in the P dot plane, which I said is more robust because more robust because these are the measured quantities. And they have done a very good job of doing a statistical analysis on various parameters of the nulling pulsars. And people who would be looking at nulling pulsars, I urge them to go and look at this paper. But one point I want to impress upon you at this point is that you see that when we look at this picture, it is not very clear to us that the nulling pulsars seem to be confined by certain death line. So now when you make this plot in the magnetic field spin period plane, then that becomes much more obvious. So the reason I wanted to show you this picture is, yes, you should always try to use quantities which are measured, not the quantities which are derived, because derivation always has certain assumptions inherent in them. But sometimes, that may give you a particular kind of insight. So which is happening in the case of nulling pulsars. So I would like to finish it here today. Thank you very much. We do not have any time, so please post your questions in the forum, and on Sunday we will talk about the glitches of the neutron stars. Thank you very much.
Thanks, Sushan, for an excellent talk, and thanks so much. That was really very interesting. And we can take a few questions. The next one is the next talk is at 12 o'clock. So if there are a few questions, we have 8 minutes. So people who are willing to sacrifice their tea can actually ask questions.
I am sorry this went a little longer than I.
No, it's absolutely fine. It actually proves that you got into the mood. That's nice.
We are, sort of, there are other people who would be giving talks. So,
No, that's okay. Luckily, we had a tea break just now. There was a tea
okay,
break.
okay. So I have eaten into the tea break.
That's all. So now my thing is at 12 in 7 minutes. So that's okay. Not a problem. So if anybody wants to ask questions, please unmute yourselves and ask. Right? Are there any questions? Anyway, we'll be meeting Sushan on Sunday again. So I don't see any questions just now, but
No.
does anybody want to ask
Not anything,
something?
not anything on this chat box.
Oh, Gitanjali. I think Gitanjali, you wanted to say
Yeah,
something. Or
yeah,
what
ma'am,
happened?
I just want to ask a very
Yeah.
small question. It's regarding the last slide. When you say, ma'am, that there is a when you have where you have plotted the time, the PP dot curve for nulling pulsars, does that mean that nulling is periodic, ma'am? So I mean, I got a little confused about that.
No. What I wanted to say is that see, what we are trying to do is, I would let me share that. Where is it? Is this the plot you are talking about?
Yes, ma'am. Yes.
Yeah. No, all I'm saying is, if we go to the previous one, you see that the nulling pulsars seem to be bounded by these death lines. Okay. And so this is in BP plane, and this is in P dot P plane. That feature is not very clear here. That is all I'm saying.
So, ma'am, what can we then say about? I mean, is there some kind of period associated with these nulling pulsars?
No. There is no period associated with the nulling pulsar. So what I am saying is that if we have various parameters at our disposal, we should try and see the behavior. We try to see correlation between various parameters. We try to see how different parameters are constraining our data in order to try and find a way to go forward. See, we really do not know why nulls happen. That question is totally unanswered. We do not know. We know a lot about how nulls happen and what happens when pulsar nulls, but we really do not know why this happens. And therefore, to go forward, one must look at various parameters and try to see if we see any correlation there, if we see any constraints anywhere, and therefore try to find a way to go forward. And in this picture, what happens is the nulling pulsars do not seem to show us that there is any sort of a particular way forward for the nulling pulsar as a population. I want to understand why this particular set of objects have nulls, not the others. So as you can see that the nulling pulsars, these are the red dots which are the nulling pulsars, and the range pretty much the same as the other pulsars, the non-nulling pulsars. So I do not, and the same in the P dot range also. So I don't immediately see any difference between the nulling pulsars and the non-nulling pulsars. That's what I'm saying.
Okay, ma'am. Thank you.
I see a question from Rohit. Why do we see familiarity between log P and log B diagram and P and P dot diagram? We will see familiarity because remember, B is derived from P and P dot. So B is proportional to the square root of P and P dot. So if you plot a P versus B and you plot a P versus P dot, you're going to get some similarities, of course, because B is derived from P and P dot. So it's not a completely different quantity. So that's why you get a similarity. Okay, so if there are no other questions, Priya, I suppose we can.
Yeah, if there are no more questions, then let's thank Sushan. Thanks for a lovely talk, Sushan. And looking forward to your Sunday appearance. And in between, people can write on the. Yeah. So we'll take a break for 2 minutes. So we'll take 2 minutes break and come back for Priya.
Okay. Thank you and bye for today then.
Thanks a lot.
Yeah, most welcome.
Yeah, just we'll start in 2 minutes. Be online.